Hello, we have one more application of differentiation to do, but that's actually section 6.5. Before we get there, we actually need to develop one more skill for finding derivatives before we can move on to that application. So I've told you in the past that using the product rule, the chain rule, the quotient rule together, using those three rules, you can really differentiate just about anything that anyone would ever give you. And in truth, it's about 95% true. There is still some types of expressions I could give you that you wouldn't be able to differentiate, at least the types that we'll see in this class. And that is when an equation or when a function for y, when a function y of x is given implicitly. So what do I mean by that? Well, I've got a whole bunch of stuff on the board behind me, so let's go through this. This is how we're used to seeing functions of x given, right? Y equals x plus 1. There's a very simple function of x, and y is, of course, the function of x. And you'd be able to differentiate this no problem. You'd say dy dx equals 1, right? So mathematically, what we say is up here in this expression, y equals x plus 1, y is given explicitly as a function of x. And what I mean by explicitly is just that y is isolated. I've got y equals, and on the right-hand side, there's my function of x. But quite often in mathematics, you're given an equation, something like here all I've done is I've moved the x over, I've subtracted x from both sides. So now I have really the same equation, just written slightly differently, y minus x equals 1. And in this case, y is still the exact same function of x, right? If you solve for y is still x plus 1. But in this case, y is said to be given implicitly as a function of x. And all that implicit means is that it's not, y is not isolated in this case. It is still, in fact, the exact same function of x. It is true that y equals x plus 1, but because I haven't isolated y is said to be given implicitly as a function of x here. And what often happens is that this is the best you can do. Of course, in this case, I can easily rearrange and isolate y, but quite often you can't do that. For example, jump down to the bottom here. Here's an equation involving x and y, e to the y plus y cubed equals 2x plus 1. And no matter how you try here, you're never going to solve for y explicitly as a function of x. It's just too hard to do. In fact, I believe in this case it's simply impossible. Sometimes it's hard and you don't want to bother, but sometimes it's just straight up impossible. But even so, written as this is, y is still a function of x. You plug in a value for x, and that outputs your y value, the y value that satisfies this equation. So jumping up to this line here, like I said, it's often hard or impossible to solve explicitly for y as a function of x. The best we can do is give y implicitly as a function of x. And even so, y is still a function of x, so we still want to talk about what is its derivative with respect to x. What is dy over dx? How do we find it? So that'll be the rest of the section. We'll just go to, I think I'll just jump straight into examples and show you by example how this works. And as always, we'll start off easy and then ramp up the difficulty as we go along. So for example, y squared plus y equals x squared. The question is, find the derivative of y with respect to x. Find dy over dx. So I don't have y given implicit, or I don't have y given explicitly as a function of x, right? I haven't isolated y. It is true that this is not one of the impossible cases. You could solve explicitly for y if you completed the square on the left-hand side. It's doable, but it's not the easiest way to proceed here in finding dy dx. So here's the idea. Here's all that goes into implicit differentiation. The idea is I'm not going to bother solving explicitly for y. I'm going to leave it as it stands, and what I'm going to do is if the left-hand side equals the right-hand side, then the derivative of the left-hand side must equal the derivative of the right-hand side. So if I want the derivative of y with respect to x, I'm going to differentiate both sides with respect to x. This is actually what you're really doing every time you find a derivative. We just don't usually think about what happens on the left because the derivative of y with respect to x is dy dx. But here, I'm just saying, take the derivative of both sides with respect to x. And this is implicit differentiation. That's all we're ever going to do. So let's go into the right-hand side first, because this is a little bit easier. Derivative of x squared with respect to x is just 2x. But what about the left-hand side? What's the derivative of y squared with respect to x? Well, you might say derivative of y squared with respect to x is just 2y. Right? Not really. That's the derivative of y squared with respect to y. Right? If you thought of that as a function of y, the derivative of y squared with respect to y is indeed 2y. So this isn't something we've had to think about too much in the past, is what we're differentiating with respect to, but here I have y as a function of x, and I want to differentiate this with I can't speak. I want to differentiate this with respect to x. So what do? Well, the chain rule comes into play here. The chain rule says if I want to differentiate y squared as a function of x, or with respect to x, well, remember what this really is. If y is a function of x, right, then what do I really have here? I have, I'm going to put it down here and then erase it. Instead of y squared, I've got a function of x all squared. Right, so what's the derivative? Well, using the chain rule on this, I should have the 2 come outside. The inside stays the same. So 2 times f of x, but f of x is y. The power lowers by 1, so it goes to a power of 1. I don't know why I'm erasing that. But then what does the chain rule say? The chain rule says I have to multiply by the derivative of the inside. So what's the derivative of f of x with respect to x? Well, it's f prime of x, right? Or remember, f of x is y, so the derivative of y with respect to x is just dy dx. So, little bit of chain rule stuff in the background there that you don't really have to worry about. All you have to know is when I'm differentiating something like y squared with respect to x, the first thing I do is I really do this. I differentiate with respect to y, so derivative of y squared with respect to y is 2y, but then multiplied by the derivative of y with respect to x. And I've very quickly brushed over why this is happening, but it's coming from the chain rule. It's coming from the fact that I actually have a function of x squared. So using the chain rule, the 2 comes outside, the inside stays the same, so the y stays the same, lowers the power by 1, and then times the derivative of the inside, so times dy dx. In practice, though, you don't really have to think about the chain rule there. All you have to remember is if you've got something involving y, differentiate it with respect to y, and then tag on this dy dx on the end. So just multiply by dy dx. So what about this one? Plus the derivative of y with respect to x. Well, first differentiate with respect to y to get 1. And then, since it's y and not x, I then tag on the derivative of y with respect to x. Which is no real surprise, right? The derivative of y with respect to x is just dy dx. And that's all the calculus. I've differentiated both sides with respect to x now. I'm done with differentiating. How do I find dy dx? Well, I need to isolate it. So how do I isolate it here? I've got dy dx common to both terms, so we'll factor it out. dy over dx times 2y plus 1 is equal to 2x. And that means my derivative, dy over dx, is equal to 2x over 2y plus 1. There is something sort of aesthetically unpleasing about this answer, and that is that my answer is still given sort of implicitly, right? It's not just a function of x. I've got this y living in here, and y is in turn a function of x, so I don't have dy over dx given explicitly as a function of x, but it really is. It really is, because once you determine x, you've determined y at the same time. So this is just something we'll have to live with. When we work with implicit differentiation, quite often our answers will involve x and y. But there it is. There's dy over dx. So I think the best way to proceed is just go through more examples. We'll do another one. All right, find dy over dx if 8x squared minus 10xy plus y cubed equals 26. So again, try as you want. It's not easy. I don't think it's even possible. Maybe it is, but can you complete the square or something here? I think maybe it is possible to explicitly solve for y, but again, not what you want to do. The easiest way is just to say, all right, I'm not going to bother solving for y explicitly. I'm going to implicitly differentiate this. So same first step as always. I just differentiate both sides with respect to x. Derivative of the left-hand side with respect to x is equal to the derivative of the right-hand side with respect to x. So we'll knock out all of the easy derivatives first. Derivative of the right-hand side, derivative of 26 with respect to x, that's just 0. Okay. What about this? Derivative of 8x squared with respect to x. Well, that's no problem. The 2 comes outside, so 8 times 2 is 16x. I'll leave the middle alone for a second. And the derivative of y cubed with respect to x, this is exactly what we did in the last example. How do I differentiate y cubed with respect to x? Well, I first differentiate with respect to y. So I get 3y squared. But then, times, the chain rule comes into play here, times the derivative of the inside, times dy dx. And if you want to remember it like that, as in, I just differentiate with respect to y and then tag on this dy dx on the end, that's totally fine. That will indeed work for you. But where it's actually coming from is the chain rule. But what about the middle here? Well, the minus 10 is just going to be minus 10 times the derivative of x times y. And what is this? Well, this is actually a product. It's a function of x times y, which is a function of x. So a function of x times a function of x, I need to use the product rule. All right, so what does the product rule say? It's going to be x times, it's the first function times the derivative of the second, so x times the derivative of the second. How do I differentiate y with respect to x? Well, I first differentiate with respect to y to get 1 times dy over dx. And then plus, product rule says now times the derivative of the first function with respect to x. Derivative of x with respect to x is just 1 times the second function, y. So the product rule came into play here, right? This is a function of x times a function of x. You have to remember that y is indeed a function of x. So, yeah, product rule, first function times the derivative of the second. So x times, how do you differentiate y with respect to x? First differentiate with respect to y to get 1 times dy dx. And then plus the derivative of the first function, so derivative of x with respect to x is 1 times the second times y. And now we're in the same boat as before. There's all the differentiation done. The calculus is done. I just need to solve for dy dx now. So we'll want to isolate this. What do we have? I'm going to keep all the dy dx terms on the left, I think, yeah. So we've got minus 10x dy dx. I'm going to cross it out, but I'm not canceling it. I'm just keeping track of what I've taken care of. So we've got that with dy dx in it, and then plus 3y squared times dy dx. So I'm taking care of that. And everything else that doesn't have a dy dx, I'm going to move it to the right-hand side. So this will be minus 10 times y. When I move it to the right, it becomes plus. So 10y, that's taken care of. And then minus 16x. Awesome. And what did I want to do? I wanted to solve for dy dx. So I've now grouped all the dy dx terms together. Now I just factor it out. dy dx times, I'm going to write the positive term first. It's a little prettier. 3y squared minus 10x equals 10y minus 16x. And last but not least, all I have to do is divide. So divide both sides to get dy over dx is equal to 10y minus 16x over 3y squared minus 10x. And there is our answer. Again, unfortunately, it's given sort of as a function of x and y, but remember y is really a function of x, so it is still just a function of x, but I do have y's mixed in here. Anything else I want to say about this? Yeah, like I said, we're ramping up the difficulty. Why is this one a little bit harder than the first one? Because I had to use the product rule there. Right? I've got a function of x times a function of x. So we had to use the product rule. But we'll keep going. So if you understood the first two examples, pause the video here, try and do this one. Try and find, as always, I didn't write it down, but find dy over dx. Find the derivative of y with respect to x. Again, you won't be able to solve explicitly for y, it's just not possible. But what you can do is implicitly differentiate this. So pause it and try, and then come back to see if you've worked it the same way as me, or at least got the same solution. So what do? Differentiate both sides with respect to x. And proceed implicitly. So what are my derivatives with respect to x? Derivative of x with respect to x is 1. What about the derivative of ln of y with respect to x? Well, what I have here is I've got something involving y, so the first thing I do is I differentiate with respect to y, right? What's the derivative of ln of y with respect to y? 1 over y. That's with respect to y. You have to keep track of what you're differentiating with respect to. So derivative of ln of y with respect to y is 1 over y. Derivative with respect to x is the first differentiate with respect to y times dy over dx. And that's the left-hand side taken care of. What about the right-hand side? Well, the right-hand side looks like that middle piece in our last example where we had to use the product rule, because I've got a function of x times a function of x. So we're going to product rule this. We've got the first function, x squared, times the derivative of the second. And we'll do this in situ here, we'll just do it on the spot. Derivative of y cubed with respect to y is 3y squared times dy dx. Right? Derivative of y cubed with respect to x is first differentiate with respect to y, 3y squared, times this extra term, the derivative of y with respect to x, plus the derivative of the first function with respect to x, derivative of x squared with respect to x is 2x times y cubed, the second function. And again, that's it. That's we've done our differentiating. There's all the calculus. I just need to isolate dy over dx now. So isolating, we'll keep this over here. 1 over y dy over dx minus, we'll bring this term over. I'm going to write the 3 out front because you tend to write constants first. 3x squared y squared dy dx is equal to, I'll keep this term first because it's positive, 2xy cubed minus 1. And I'm going to do this all in one go here. What does dy dx equal? Well, I'm going to factor it out. So I've got dy over dx times 1 over y minus 3x squared y squared, and then we're going to divide by that. So we're going to have the right-hand side 2x y cubed minus 1 divided by this factor. So what did we factor out? 1 over y minus 3x squared y squared. And I claim that this is our answer. So I'm just looking for any tricks we might do. You might want to make this look a little bit prettier so you don't have a 1 over y term. Maybe multiply top and bottom by y. Right? You could do something like, I'm going to multiply the entire top by y. 2x y to the 4th minus y. So I multiplied everything on top by y, divided by, multiply everything on the bottom by y. So 1 over y times y is 1 minus 3x squared y cubed. And if you enter that into MyMathLab, it would recognize that's equivalent. It would accept that as well. It's a little bit of a prettier answer. Here's other tricks you could do. Other tricks you can do to make your answer potentially look a little prettier. You don't have to, and I don't think it makes it look any prettier in this case. But x squared y cubed, what does x squared y cubed equal? Well, remember up here, x squared y cubed equals x plus ln of y. So you can do tricks like this that sometimes help your answer look nicer. Instead of having x squared y cubed, I'm going to replace that with x plus ln of y because I know they're equal. So this would be 1 minus 3 times x plus ln of y. In truth, I think I've made it look worse, but I'm just pointing out that things like this you can do. These are little tricks that sometimes you make use of. But either way, they are all algebraically equivalent. So MyMathLab should accept them all. Okay, so we'll spruce up our example here a little bit. Instead of just asking to find the derivative of dy over dx, the question is find an equation for the tangent line to this curve. Of course, this curve right here, this equation, if you tried to isolate y, you'd have trouble. But what I want to do is if I want to know the equation of a tangent line, I need two things, right? I need a point on the line. Well, here's my point, 4, 2. But I also need the slope. And the way we find slopes is we compute the derivative, dy over dx. That'll give us our slope at any point, and then we just plug in the point 4, 2 to get the slope at that particular point. Alright, so I'm not going to be able to explicitly differentiate this. I can't explicitly solve for y, but that's okay. We'll just continue as we've been doing. We'll implicitly differentiate. And what I'm going to do is always, I won't write this step down in the interest of space. We're just going to differentiate both sides with respect to x. Alright, so we differentiate. Yeah, I guess I'll write it. We can make the space work. And this will actually look a little bit nicer writing it like this because remember, every time we deal with square roots, we convert them to exponents. It's much easier to differentiate. So I'll at least take this opportunity to write that as x to the 1/2. And differentiate the right-hand side with respect to x. Okay, so exact same equation, but if the left-hand side equals the right-hand side, then the derivative with respect to x of the left-hand side should equal the derivative with respect to x of the right-hand side. Now we'll go ahead and differentiate. Derivative of y with respect to x. Well, remember y is implicitly a function of x, so first thing I do is differentiate with respect to y to get 1, and then times dy over dx. Plus, what about this? Well, here I've got a quotient, right? A ratio, x to the 1/2 over y. One thing I could do is I could write this as x to the 1/2 times y to the -1 and then proceed with the product rule, as we did in the last example. But I'll leave it as a quotient. We'll get some practice with the quotient rule in. So the derivative of a quotient, we use quotient rule. What is it? Low, D, high, so bottom, y times the derivative of the top. Derivative of x to the 1/2 minus high D low, the top, x to the 1/2 times the derivative with respect to x of the bottom, y, all over y squared. And that should equal what? The derivative with respect to x of 3, derivative of constant is just 0. So 0. And unfortunately, I really don't have a whole lot of space here. I'm going to have to erase and then come back up. I will save this. I want to save the point we're looking at, so it's the point, I'll just keep it written here for my own memory, the point 4,2. But what we're still trying to do right now is just find dy over dx. So I still have some differentiating to do, right? I haven't evaluated these derivatives yet. We've got dy over dx plus, what do we have? Y times derivative of x to the 1/2. 1/2 comes out front, so 1/2 times x to the minus 1/2. 1/2 minus 1 is minus 1/2. Minus x to the 1/2 times the derivative with respect to x of y. We actually already did that, right, in this very first step. I should erase this entire line so it's not so ugly. Sorry about that. We already did differentiate y, right? First, differentiate with respect to y to get 1 times dy dx. So I'll just write dy over dx. And this is all over y squared, the bottom squared, equals 0. So I've seen this many times in this class and other calculus classes. At this stage, students have a little bit of trouble isolating dy over dx. It's not uncommon. And the reason it's sort of a little tricky here is because this one's free by itself, but this one I want to sort of get out, and right now it's stuck in this quotient. Right? It's stuck in part of the numerator of this quotient. Lots of ways you can handle this algebraically to sort of get it out of this quotient, and then we can group it with this one and isolate it. The way I'm going to proceed is I'm just going to clear both sides of fractions. So this denominator over here, let's multiply both sides by y squared to get rid of it. So we'll multiply both sides by y squared. Multiply this term by y squared dy over dx. And then this whole thing gets multiplied by y squared, so the bottom goes away. And this will be, I'm gonna write this in a different manner. This is y over 2, and this becomes the square root of x down at the bottom. So that's this term, minus square root of x times dy over dx. And that equals 0 times, remember I'm multiplying both sides by y squared, but 0 times y squared is still just 0. Now we're almost there. I think we'll do this in 2 more steps. Dy over dx, if I factor it out of the terms that have dy over dx in it, what do I have? I've got y squared minus square root of x. And this term, we'll just move this to the other side. This is minus y over 2 root x. And I promised we'd be done in 2 more steps, so we'll wrap this up right here. Dy over dx then is this expression divided by y squared minus root x. But when you divide by it, the way you divide fractions, if I wrote this one fraction divided by another, you flip and multiply. What ends up happening is this just ends up in the bottom over here. You can check that if you don't believe me on the algebra. So this is just minus y over 2 root x times y squared minus x. There is our derivative. You might want to think about cleaning this up a bit if you could see some way to clean it up looking back at the original expression. I don't really see much we would have done though. So what I want to do now is this is my slope at any point xy, right? I want to know the slope in particular at the point 4,2. So we'll evaluate this derivative at the point 4,2. The notation people would often use here is something like this. Dy over dx evaluated at 4,2. So the bar on 4,2 there. That equals, now we'll just plug in 4 everywhere we see x, and 2 everywhere we see y. So we're looking at minus 2 over 2 root 4 times 2 squared minus 2. whole bunch of 2's here. What do we have? This is, let's cancel this with this. So we've got minus 1 up top, minus 1, we can fix this, there we go, minus 1 over, what do we have? 2 times 4 minus 2, 2 times 2 is minus 1/4. And that's really what we wanted, right? We didn't just want the derivative. It wasn't just a question of find the derivative dy over dx. It was actually find the derivative at the point 4,2 so we can find the slope of this tangent line. And now we just have to write down the equation of the line, which will harken back to when we reviewed lines and how to write down the equation of a line given certain pieces of information. And you'll recall we had the point slope form, right? If I know a point on the line and the slope minus 1/4, then I can write the equation of the line. The general form is y minus y naught equals m times x minus x naught. M is the slope, x naught, y naught are the known coordinates of a point on the line. So what we're looking for is y minus the y coordinate 2 equals the slope minus 1/4 times x minus the x coordinate 4. And I think this is a totally acceptable answer, but quite often my math lab will specify things like write y equals something, so give your answer in slope intercept form. So we'll give this in slope intercept form as well. We'll solve for y. Y is, what do we have? We got minus 1/4 times x. Minus 1/4 times minus 4 is plus 1. And then when I move this minus 2 over, that becomes plus 2. So last but not least, we're looking at minus 1/4 x plus 3. And so a little bit more involved than just finding the derivative. The bulk of this is indeed implicit differentiation, find dy over dx, right? We're using this new technique, this implicit technique. But that is the bulk of the work, finding the derivative. Then we had to know the slope at the point 4,2, so we evaluate the derivative at 4,2, because derivatives tell us slopes at any point that we want. And then we plug that information into our standard point slope form for a line. We'll do one more example here. One more example that's sort of more business geared. Alright, I'm going to give you a demand function. The demand for a product is given by ln of q equals 1 minus 0.44 ln of p. The question is find the price elasticity of demand. So, what do I really need here? You might think I need to solve for q explicitly to plug it into that piece, but we'll see down the road that we don't actually need that. Let's focus on the bulk of the question here. I clearly need the derivative of q with respect to p. So let's try to find that. And one thing you might do, and this would be totally acceptable in this case, it's really not hard to solve explicitly for q. Right? If ln of q equals this, that means q is equal to my base e to the 1 minus 0.44 ln of p. But that sort of defeats the purpose of what we're doing, so I'm not going to do that. I'm going to leave this as q is implicitly given as a function of p, and we're just going to differentiate. So we differentiate both sides with respect to p. Derivative with respect to p. Okay. And now we differentiate. So How do I differentiate with respect to p? Well, first I differentiate this with respect to q. So ln of q with respect to q is 1 over q times the derivative of q with respect to p. And on the right hand side, what do I have? Derivative of 1 with respect to p is 0, and derivative of 0.44 ln of p with respect to p is minus 0.44 times 1 over p. So we'll solve here. We'll solve for dq dp. dq over dp is just multiply both sides by q. So minus 0.44 q over p. Awesome. There's the derivative of q with respect to p. And that's what I needed to plug into here. So let's plug it into there and see what happens. My elasticity is minus p over q times dq over dp, which we just found, is times minus 0.44 q over p. Notice, by the way, I put that in brackets because otherwise it wouldn't look like multiplication, it would look like I'm subtracting this off. And the reason I said we actually, in this case, don't need to solve for q explicitly is because I knew this was going to happen. Those q's cancel out. Actually, so do these p's. So my elasticity is constant. It doesn't depend on the price at all. It is always 0.44. Is that elastic or inelastic? Well, it's less than 1, so this is inelastic. All right, so that really is our last technique for differentiation. And truly now, using this as well, when we add this to our toolbox, truly anything anyone could ever give you, excluding some more fancy functions outside of the scope of this class, truly anything anyone could ever give you, you can find the derivative of it using all these techniques. And this technique in particular, implicit differentiation, we're going to use that in the next section, 6.5. Thanks.